Okay, so now we discuss on the dynamic bearing capacity of shallow foundation. Okay, on this discussion, okay, we may discuss on the same way with the static approach. Okay, so for the first, we discuss or recap again. Okay, on the static bearing capacity of a shallow foundation. Okay, and then we discuss on the sand material, okay, under a dynamic or vibrations load. Okay. Then we discuss on what we call as on the uh, clay material. Okay. The next will be the discussion on the transitions loads. Okay. And the last one, we discuss again on a granular type of soil under dynamic load, where the discussion is more related to the bearing capacity and also on the settlement. Okay. So, however, the discussion of the sand clay is very straightforward. Okay. So, whereby they just reduce a number, for example, of the p value and also increase or multiply with coefficients for the bearing capacity for the clay value, for the clay calculations or formula. Okay, so means that we still rely on the same concept of the static. Okay, so however there will be some difference in terms of the soil properties. Okay, which is either we reduce the value or we increase the value for the soil properties to gain the bearing capacity value for the shallow foundations. Okay. Okay, the function of the foundation is to transmit load from superstructure to substructure. Okay, before a foundation can be designed, it's essential to understand the theory of ultimate bearing capacity. Okay, for this case, I will not discuss by using the Eurocode or EC7. Okay, so the discussion will be on our next topics later on. Okay, so this is just to relate the dynamic loads with the static load using the common type of bearing capacity equations. Okay. So ultimate bearing capacity is defined as the smallest pressure that causes shear failure to to soil supporting the foundations. The Zagi bearing capacity and Mayoff general bearing capacity equation will be discussed in this chapter. In addition, it will be assumed that the soil supporting the footing is homogeneous and relatively dense or firm, and the failure mode of the soil is categorized as general shear failure. So that's the assumption made by Tzagi, okay, or Meyerhoff, okay, in order to use their equations. Okay. So first, the soil is assumed to be homogeneous, okay, and dense or firm, okay, and the general shear failure will be the failure modes of the soil. Okay, two important aspects must be considered in foundation design. The load applied to the foundation should not cause shear failure to soil supporting it. The foundation soil should not undergo excessive settlement. Okay, as we have discussed previously, okay, the functions of the design is rely on the SLS and also ULS, serviceability limit state and also limit state. Okay, in most cases, however, settlement is the governing factor in foundation design. So the static bearing capacity of foundations has been extensively studied and reported in the literature. However, foundation can be subjected to single pulse dynamic loads which may be in vertical or horizontal directions. Okay. So the dynamic load due to nuclear blasts are mainly vertical, and from the earthquake, okay, the horizontal dynamic loads on the foundations are observed. Okay. This type of loading may induce large permanent deformation in foundations. Isolated column footing, strip footing, mat footing, and even pile foundations all may fail during seismic events. Okay. Such failure are generally attributed to liquefactions. Okay. So the meaning of the liquefaction is a conditions where the mean effective stress in a saturated soil reduced to zero. Okay, so it means that the soil will behave like a liquid or like a water. Okay, because the effective stress is reduced to zero. Okay. However, a number of failures have occurred where field consolidation indicate there was only partially saturated or a dense soil, and therefore liquefaction alone is a very unlikely explanation. Okay, so there will be another justification. Okay, so it is not 100% due to the liquefaction effect. Okay. Rather, the reason for seismic settlement of this foundation seems to be that the bearing capacity was reduced. Okay. So, in order to design, which is related to the seismic, okay, so we need to uh, need to have some changes, okay, on the soil properties itself, okay, um, whereby we can increase the bearing capacity later on. Okay. Though large amount of information, though large amount of information on dynamic bearing capacity foundation is available in literature, it is mostly based on theoretical procedure and not supported by field data. Okay, so there is a lack of uh, information on the dynamic bearing capacity study. However, one must keep in mind that during the analysis of the time-dependent motion of the foundation subject to dynamic loading or estimating the bearing capacity under dynamic condition, several factors need to be considered. Okay. Most important of these factors are nature of variations of the magnitude of the loading pulse, duration of the pulse, and strain response of the soil during deformations. Okay, so all of these factors has been included. Okay, in the explain in the justification by Das. Okay, so in that sense, he come up with the some modifications. Okay, on the soil properties. Okay, for example, on the sand and also on the uh, clay. Okay. So for shell, okay, this is a brief explanation on shallow foundation. Okay, shallow foundation is the foundation whose depth below the surface Z is equal to or is less than least dimension. Okay, so Z is the depth while B is the dimensions of the foundation or shallow foundation. So B is greater than Z. Okay, so it means that the effective area, okay, on the shallow foundations is not greater than B. Okay. So types of shallow foundation. Here we have a pad footing, strip or continuous footing, and rough or matte foundations. Okay. So for the pad footing, generate an individual footing designed to carry a single column and loads, although there are occasions where the pad foundation support two or more columns. Okay. So then we have here strip or continuous footing. Often termed a continuous footing, this foundation has a length significantly greater than its width. It is generally used to support a series of columns or a wall. Okay, so that is the strip footing, because in the Meyerhof or in the Terzaghi, okay, so there will be a deep, the equation is based on the type of the foundation or the shape of the foundation. So either pad footing or strip footing, okay, will they have their own different type of equations. Okay, however, for the matte or rough foundation, okay, I guess it, it has been discussed by Prof. Khairul previously. Okay, there is a generic terms for all types of foundation that cover a large area. A rough foundation is called as a matte foundations. Okay, so factor in the design, adequate design, limiting settlement, safe against shear failure. Okay, so this is the common type of factor that need to be considered in the shallow foundation design. Okay. So adequate depth, the depth of the footing must be sufficient to prevent any changes in surface conditions, horizontal load, and strong overturning moment. So there will be some conditions, okay, especially in area that experience negative temperature, okay, to prevent frost again and frost action and volume change effect. The depth of the foundation should more than 1.2 and 1.5 respectively. Okay. So this is some value for the limiting settlement. Okay, the guideline by Scampton and McDonald in 1956. Okay, where the sand, the maximum total settlement should less than 40 and clay should less than 60 for the shallow foundations. Okay. Safe against shear failure. Okay, so this is to prevent for any failure. Shear failure occurs when the soil divides into separate block or zone which move fully or partially and tangentially with respect to each other along slip surface. Conventionally, the factor safety to use in design against shear failure is more than 3.0. Okay, so this is the based on the typical type of design. Okay, so when it comes to EC7, okay, there will be slight changes, okay, on the factor safety value or in terms of their approach. Okay, so I will try my best to share it on the next following class. Okay, okay. So this is a type of mode of shear failure. Okay, so actually this is one a part of my PhD study. Okay, so I'm using digital camera, okay, DSLR, and then capture for the soil movement. Okay, so during the loading process, okay, we capture at least 1 frame per second. Okay, so until it reach 20 millimeter of displacement, okay, which is 0.2% or 20% from the footing width. Okay, then from this study, okay, I come up with the vector observation, okay, by using particle image velocimetry methods. Okay, so by the use of the MATLAB software and some algorithms has been developed, okay, then I come up with this kind of shear failure modes patterns. Okay, so this is a common or typical type of Prandtl failure mechanism, okay, that has been proposed in 1921. Okay, so after almost 90 years, okay, so uh, I yeah, we can observe the failure mechanism accurately, okay, by knowing what is the value or the magnitude of each vector. Okay, so previously, some of the researcher, okay, just using, for example, a clay, a coloring process, okay, or by using a noodle, okay. So they put a noodle in front on the soil before the perspective view panel, okay. So then they can observe for the patterns. Okay, however, it is not very accurate because it doesn't show for any movements of the vector. Okay, so this is the most accurate methods. Okay, then we can produce for the contour, vertical displacement, and also for the horizontal, and we also can estimate or determine the shear strain, okay, at the failure. Then a comparison has been made between this, what we call as a vector from the laboratory scale with the commercial software, okay, to look or to validate the result. Okay, so the findings show that a good agreement between the laboratory result with the one produced by the software. Okay, so this is a common type of general shear failure for an homogeneous and firm material. Okay, so yeah, this is the common type of shear failure. Okay, this occurs when a clearly defined slip surface formed under the footing and develop upwards towards one or both sides and eventually to the ground surface. Okay, so there will be two more types of shear failure. They call as a local shear failure. Okay, significant vertical movement may take place before any noticeable development of shear plane occurs. Okay, normally for material that is not dense or packed well. Okay, so then we have another types, a punching shear failure. Okay, this is downward movement of the foundation caused by soil shear failure only occurring along the boundary of the wedge of the soil immediately below the foundations. Okay, so this is more related to over what we call a multi-layer of soil. Okay, which is normally this happen when the soil is loose, and then there will be a underlying soil that has a very dense uh, impact conditions. Okay.
Doktor,
Ah,
as in kalau in a sinkhole, we can consider it as punching shear failure ke? Sinkhole
uh,
in limestone. This is quite a like a idiot
So
Uh,
it's a very direct, direct.
direct as in like macam sinkhole kan, the soil suddenly like dissipated beneath the ground, and then the anything on top can be like vertically moved downward in
Mm.
a quite immediate manner.
I guess this is more related to a vertical loading on the top of a layer soil,
Oh, okay,
while
okay.
for the single is due to the voids inside the soil.
Yeah, the void inside the soil.
So I guess it is a different
Meaning,
condition.
okay, sorry. Okay.
So it's more related to voids that occur in the soil compared to this one. This is due to the vertical load applied on the layered soil. Okay, Intan.
Okay, doctor, thank you.
Okay. So this is a typical bearing capacity of soil. Okay. Um, so this is common equation from Meyerhoff. So actually, in the EC7, okay, there will be slight changes, a little bit changes in terms of the factor itself. Okay. Okay. Oh, sorry. Okay. I, I will give a new version of this one because I could not amend for this error. Okay. So this is the shape factor, depth factor. It rely on d f over b. Okay. Greater or less than 1. So then we have an inclination factor. Okay. So in EC7, okay, they also include the eccentricity, okay, and the inclination factor in the one equation. Okay, so we may explore on the next class. So both Terzaghi and Mayoff ultimate bearing capacity consists of three terms. Okay, we have CNC, QNC, AQNQ, and gamma, B, and gamma. Okay, which is actually from this equation. Okay. So C is referred to the soil cohesion below the base of the footing. Okay. So if we can draw, okay. So this value is C and this value is gamma, while this value is gamma for the Q. Okay. This value for gamma for the next. So this is first equation, sub equation. This is second sub equation, while this is the third sub equation, the Meyerhoff. Okay. So this is the first, second, and third. Okay. Okay. So this is one of example. Okay. It just to uh, recap again on your on what we understand on the uh, static load. Okay. So consider the diagram of shallow foundation as shown. Calculate the allowable bearing capacity using Mayer equation for the following condition, assuming vertical load will be applied. Use a factor safety 3.0. So the first ground table is at the base of the footing. Okay, the ground table is 1.3 below the ground surface. So the second one, sorry. So if 1.3, so this will be 0.5. Okay, so the first one is at the base, the water. So the second one is at the below the 0.5 below the footing. Okay. So there will be a difference of approach. Okay, if we have a groundwater uh, in the ground. Okay, so we need to use a three different approach actually. Okay. So okay, the reader are reminded the 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 presence of the water table will require three different situations, okay, to be considered in calculation. These considerations are applicable to both Meyerhof and Terzaghi bearing capacity. Okay, the water is located between ground surface and base of footing. So this is the equation should be used. Okay, so for the first situation, okay, so it is between the ground surface and base of the footing. This is so the effective unit weight must be used, okay, for the condition where the groundwater is below, eh, for the soil below the groundwater level. Okay, the water table is located between the base of the footing, but the distance d from the base of the footing to the water level is less than or equal to the width of the footing. So in this situation, the b is equal to 0.8. Okay. So the groundwater level for the second problems, okay, is within the value of b, okay, because the b is equal to 0.8. Okay. So then we may use this equation, okay, to include the effect of the groundwater level. Okay. So what will be affected on the groundwater table is, okay, so let's say if it is between the surface and the base, okay, the equation of 2 and 3, okay, will be uh, affected, okay, okay, and if the condition where the groundwater level below the base, okay, only the third equation will be affected, not the second sub equation. So the water table is located below the base of the footing and the distance d between the water table and the base is greater than the width of the footing b. The ground table does not affect the bearing capacity. Okay. So if greater than b, so for example, it located here, okay, which is uh, greater the depth the depth is greater than the b below the base, so no need to consider the effect of the water level. Okay. So this is some of the and this is a calculation for these problems. Okay. So first we need to determine. Sorry, this is the fee. Okay, sorry. This is 40 NC obtained from the table 2. So obtained uh, is NC 75.42 and Q 64.30 and gamma is 109.60. Okay, then we just calculate all the equation here for the shape factor and FQS, F gamma S. Okay, then we need to choose which equation for the depth factor. Okay, for this case, df over b is less than 1 or equal than 1. So then we use this equation, get the depth factor value and also the inclination. Okay. So because the beta is 0, there is no vertical, there is no inclinations. Okay, so FCI, FQI and gamma I is equal to 1. Okay, so later on there will be a slightly changes on the gamma because the water is at the base of the footing. Okay, so there will be no difference of this one. Okay, because it is at the base, not between what we call as the surface and also the base. Okay, so no need to have changes for this unit weight. So we use 17.5. Okay, so use the 17.5 as usual. Okay, so there will be a difference of this one. Okay, we need to use the effective stress value. Okay, which is the 19 minus with 10. So 10 is the unit weight of water. Unit of water is equal to 10. Okay, or if you want to use 9.81 or 9.1, so it's still acceptable. Okay, but to make it easy in the calculation, so we use 10. Okay, so later on we obtain 582.5 for the allowable or design loads after divide with factor safety of 3. So that is for the water at the base. Okay, so now, okay, if the water is 0.5 below the base, okay, the reader are reminded that adjustment must be made to the unit weight in the gamma terms as the distance of the water table measured from the base of the footing is less than the width of the footing. Okay, so this is the equation which is affected the sub-equation number 3. Okay, so number 2 doesn't have any changes. Okay, so gamma effective plus D. Okay, D is the depth of the water from the base. So from this case, okay, 0.8, the total is 1.3. So 1.3 minus 0.8 is equal to 0.5. 0.5, okay, and then over 0.8 is the width of the footing. Okay, 17.5 is the value for the soil or unit weight of the soil above the groundwater level minus with the effective unit weight, which is 19 minus with 10. So come up with 14.31. Okay, so later on the QU is equal to 1987.01. Then divide with the 3 from the what we call as from the factor safety, and then obtain 657.67 for the bearing capacity of the soil for case number 2. Okay, so that is for the uh, static load. Okay, so now we move to the uh, dynamic load. Okay, we go for the sand first. Okay, so this is the common type of equation from Meyerhof. Okay, so in sand with C is equal to 0, so we can eliminate the first part of the C of the sub equation of the equation. Okay, so it become like this. Okay, so what will be the difference between the static and also the dynamic? Okay, very straightforward. Okay, when I read the explanation is, yeah, it's very straightforward explanation. Okay, when it rely on the previous research, okay, carried out by some of researcher. Okay, so this is the same NQ and N gamma, okay, that will be used, okay, for the dynamic as well. Okay, it just have a change of the phi value. Okay, okay. So the the preceding equation for static ultimate bearing capacity evaluation are valid for dense sand, okay, where the failure surface in the soil extend to the ground surface as shown in 6.1. Okay. This one, okay. And that is what is referred to the as the case of general shear failure. Okay. So, however, okay, if the relative density of the soil, the granular soil RD is less than about 70%, local or punching shear failure may occur. Okay. So this local and punching shear failure is contribute from the low density of the soil, which is 70%. So normally for high density, we consider as more greater than 70%. Okay. So when the relative density is less than 70%, so they will so we need to do some uh, calculation, okay, to get the new or the effective friction angle. Okay. Here's for static ultimate bearing capacity, if zero is the RD, okay, RD less than 0.67, okay, the value of the phi in should be replaced by the modified friction angle. Okay, so this is the value of the friction. Relative density. How to determine the relative density? Okay, so we should use a relative density test by using a shaking table. Okay, so you need to look on the standard. Okay, on how to determine for the relative density of a sandy soil. So we need to find the maximum density and also the minimum density. From there, we can calculate what is the relative density. So then after we do the correction, so we obtain the new relative density. But this is still under a static approach. Okay, sorry. Okay, so this effect correspondent to a decrease in the angle of friction of soil by about degree when the loading velocity reach a value of about 50.8 times 10 power by negative 3 millimeter per second. Okay, so does refer to, I'm not sure who is the researcher, okay, for this result. Okay, and then he found out that when there is an occasions of a vibration, okay, so the sand properties, especially on the phi value, will be reduced, okay, by 2. Okay, so in that sense, okay, for a typical uh, phi value for a sand, let's say 30, okay, so when the soil experience a vibration, okay, or any magnitude of vibration, okay, uh, we need to reduce from 30 to 2. Okay, so later on, we may obtain 28, and then there will be a difference of the N gamma, NC, and NQ. Okay, because the value has been reduced from 30 to 28. Okay, okay. So that is a finding from the dust. Okay, so if you want to cater for the dynamic response on the sandy material, okay, so we need to reduce the amount of the phi from whatever value minus with 2. Okay, so this is an example, okay, uh, for the sandy material, okay, a square foundation, if a dimension b times b has to be constructed on a dense sand, okay, so there will be no difference. There will be no difference of the phi, okay, due to the density of the soil. Okay, if the depth is 1 meter, okay, its depth is 1 meter. Okay, the unit weight and the static angle of friction of the soil can be assigned representative value of 18 kilonewton per meter cube and 39 respectively. So the foundation may occasionally be subjected to a maximum dynamic load of 1,800 kilonewton, increasing at a moderate rate. Okay, so there will be a, dynamic loads, okay, in a moderate rate. Okay, determine the size of the foundation using a safety factor of 3. Okay, so we need to find what will be the value of B, okay, after the foundation has been subjected to a dynamic load. Okay, so we know what is the value of the load applied. Okay, so the load will be uh, is represent the QU, which is 1,800. Okay, then we also been provided with the phi value, which is 39, and the unit weight of 18. Okay, so when we sketch the problems, okay, it will be like this one, okay, where the df is equal to 1 meter. Okay, so we need to identify the b of the square footing. Okay, so the b is equal to b, yeah, b square. The size is equal to, the area is equal to b square. Okay, the factor safety for this case is equal to 3. Okay, okay. Given that 3 is equal to 39, in the absence of any other experimental data, for minimum ultimate dynamic bearing capacity, okay, so phi dynamic is equal to phi minus with 2, okay, then 39 minus with 2 is equal to 37. Okay, so by using the equation here, okay, for the sand material, okay, okay, so this is the value, this is the equation that we may use. Okay, before that, okay, we need to identify what will be the NQN and gamma. Okay, so from 39 to 37, okay, so then we may look on this diagram. So 37 is equal to NQ 42.92 and N gamma 66.19. Okay. So that is for the NQ, for the phi 37 and also the N gamma. Okay. So then include what we call as the shape factor, okay, and also the depth factor, and also the uh, dy, dx, sorry, d gamma, and also the inclination factor, okay, in the uh, result. So first we just estimate, okay, let's see, okay, we have two type of depth factor here, okay. For the depth factor, uh, actually we doesn't know what will be the what will be the B, okay. So as a try and error, okay, we use the D over B less than 1 first. Okay? So when we use D over V less than 1, okay, then later on we may check again with the result of the B and then calculate for df over B, either it is less or greater than 1. Okay. So then this is the equations that we achieve. Okay. 1355 plus 2 3 plus 2 3 323.9 over B 357.4 B. Okay. So with the factor safety is equal to 3, okay, and the area is B2, okay. So then we obtain the final equations. Okay. So this is actually the stress. Okay. We want to get the Q. Okay. The Q is the load. Okay. The load that we have here is 1,800. Okay. So to make it to be as a stress, okay. So this should be multiplied with the factor safety and also divide with the area. Okay. So later on, this will be the final equation, okay, where we include the value of the QU, okay, on the left side and the rest on the right side. Okay. So the author used the try and error methods. Okay, then they found that the value is equal to 1.6 meter. Okay, so actually we can get the value, okay, by just insert in the calculator, okay, and then we can get exactly the value without doing this kind of try and error. Okay, I also not sure. Yeah, I still I'm not remember the procedure. Okay, but I guess most of you know how to use the calculator and then include in the and then just put all the equation in the calculator to estimate the value of the B. Okay. So when we divide the df over B, okay, so it is less than 1. Okay, so means that the 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 depth factor, okay, is suitable uh, to be used, okay, um, where the df over B is less than 1. Okay, so the value of the B is equal to 1.6. Okay, so that is for the sand material. Okay.
Dr.
Ah,
One question. Based on this dynamic load, are we assuming the velocity reach a value of that 50.8 times the power of -3 for this example? Because the question doesn't say.
yes, it doesn't mention,
Yeah,
but I guess 50.8 times 10 pi 10 power by negative is very low. Okay, so
it's okay.
yeah, whatever value uh is greater than that, so they consider also it should minus with 2 for the fee.
So 2 phi is the constant value, or it will increase according to the loading velocity?
Yes, yes.
Oh,
If you
okay.
want to get it accurately, we can use this what we call this result. Okay,
I see.
for
So for
example,
this example, we are assuming it reach a minimum floating velocity lah.
Yes, yes.
Okay, understand.
Yeah, for example, if we are provided with a number of velocity and then the type of the dry sand, so might be we can use this diagram to estimate what will be the what will be the reduction of the p value.
Okay, thank you, doctor.
So that is for the sand material. Okay. So then for a bearing capacity in clay, okay. So due to the phi value is equal to 0, okay. Let me check. Let me check. Okay. So the n gamma will be equal to 0. Okay. So only for sub-equation number 1 and sub-equation number 2, okay, will be used for these equations. Okay. So there is no sub-equation number 3. Okay. Because the n gamma is equal to 0. So now commonly the NC is 5.14, okay, for a pure clay without any C value, without any phi value. Okay. So the only difference between equation number 1, equation number 2 is due to the df over b. Okay, if the df over b less than 1, so this is the full equation. If the df over b is greater than 1, so we may use the next equations. Okay. So the ultimate bearing capacity of foundation resting on saturated clay soil can be estimated by using equation, provided the strain rate effect due to the dynamic loading is taken into consideration in the determination of the undrained cohesion. Unlike the case in sand, the undrained cohesion of saturated clay increase with the increase of the strain rate. Okay. Based on those results, okay, Carroll 1963 suggested that the ratio between the CU dynamic over CU static may be approximated to be about 1.5. Okay. So definition of the strain. Okay, this is the definition of the strain rate. Okay, under the foundation. Okay, where we monitor the increment the rate of the strain. Okay, by monitoring the settlement occur on the below the, the below the soil. Okay, and then the difference is in terms of the value of the CU. Okay, where the CU increase slightly 1.5 compared to the static value. Okay. So that is what has been addressed by Das in his reference book. Okay, so it means that there will be an increment of CU, okay, due to the dynamic. So means that we may use the 1.5 times the CU for the static to represent in a dynamic conditions. Okay, so there will be a difference of the CU, okay, but the rest will be same. Okay, so it's very surprisingly, but that is the way how does describe this the effect of the dynamic in the clay soil. Okay. So there is no example of these conditions. Okay. Okay. Now we look on the behavior of foundation under transient load. Okay. okay, they just want to describe, okay, what will be happen if the condition of the dynamic load increase to the maximum, okay, and then have a constant uh, dwell times, okay, and then reduce, okay, the value with times, okay. So a limited number of laboratory tests for observations of load settlement relationship of foundations under transient loads are available. Okay. The experimental evaluation of these tests are presented in this section. Okay. Load settlement observations of square model footings resting on sand and clay and subjected to transient load have been presented by Carney and Sloan. Okay, so they use a model with a size of 114.3 to 228.6 millimeter square and were placed on the surface of the compacted soil layer. Okay, the transient load to which the footing was subjected of the nature. Okay, the nature of the settlement of footing with time during the application of dynamic load is also shown in the same figure. Okay, so they recorded also the footing settlement. Okay, after the load, after the soil has been applied with a dynamic load. Okay, so the what we call is the maximum settlements occur, okay, during the constant load, okay, compared to the maximum value of the dynamic loads. Okay. So in general, okay, during the rise time, which is the TR of the dynamic load, okay, the settlement of a footing increase rapidly. Okay, so actually they test on both sand and also on the clay materials. Okay, once the peak load is reached, the rate of settlement with time decrease relatively. Okay, however, the total settlement of footing continues to increase, okay, during the well time of the loads, which is under a constant loads, and reach a maximum value as max at the end of the dwell time. Okay. During the decay period of the load, okay, when they reduce the number of the load, the footing rebound to some degree. Okay, so they reduce the number of the settlement. Okay, so this is the result, okay, obtained between sand and clay material under the transient load. Okay, so this is the result from the static QU for the sand, and this is the result under the maximum loads. Okay, so then when we divide the QD with the QU, okay, so this is the 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 the, the difference, okay, between both value under dynamic and under static. Okay, so this is the time during the rise, dwell, and decay periods. But this is the result, okay, for the settlement. Okay, and this is the result for the clay. Okay, so we can the QU is the static, the Q max is the during the what we call during the maximum value of the dynamic. Okay, and the QD, okay, where's the QD one, is the during the 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 dwell periods. Okay, so they divide difference, okay, for the clay material. Okay, this fact show that for a limiting settlement condition, a foundation can support higher load under dynamic loading condition than those observed from the static test. Okay, so that is finding has been made by DAS, okay, based on these transient loads. Okay, okay. So dynamic load versus settlement prediction in clayey soil. Okay, so this there is another study. Okay, it's been made by Jackson and Hadala, okay, in 1964. Reported several laboratory tests. Okay, this is the size of the footing, highly saturated compacted plastic, okay, buckshot clay. That is the type of the clay. Okay, the tests were similar in nature to those described previously in this section. Okay, based on this result, Jackson and Handala have shown that there is a unique non-dimensional relation between QD max over B square CU. Okay, this is the relation. Okay, and S max over B. Okay, CU is the undrained shear strength. Okay, based on TD equal to 0. Okay, however, for dynamic load with TD, the result will not be to a difference. Okay, so there will be no two different when the TD is greater than 0. Okay, so this is a result during what we call as during the dynamic based on the uh, pattern that they or the graph, okay, based on these two non-dimensional equations. Okay, okay. Jackson and Handala have recommended the following procedure for the proposed. Okay, so now this Jackson and Handala, okay, based on the pattern that they have proposed. Okay, so then, okay, they come up with a relation, okay, between the static load, okay, versus settlement relationship for the foundation from plate bearing test in the field. Okay, uh, determine the unconfined compression strength of the soil QU in the laboratory. Okay, which is QU equal to 2 CU. Okay, then he plot a graph of Q over B square CU versus static over B. Okay, so for any given value of static over B, then he multiply with the Q B square CU by the strain rate factor 1.5 and plot it in the same graph. Okay, the resulting graph of S static over V versus 1.5 Q over V square CU will be the predicted relation between QD max over B square CU and S max over B. Okay, so first um, use the value from the static load and then plot for a graph of relationship here. Okay, then in order to what we call as to predict, okay, what will be uh, the the dynamic effect, okay, uh, based on the static approach. Okay, he just multiply with 1.5, okay, of the value. Okay, so that's in that case we can find out that the this is the difference of x, and then he extend to 0.5. It means that he just multiply with 1.5 for 1 point. Okay, and the same goes here. Okay, where he know the distance of x and then multiply with 0.5 to get for another value to estimate or to predict of dynamic load settlement receipt for a foundation on a clay layer. So I guess 1.5, the value that we have discussed previously, okay, on the strain rate factor. Okay. So yeah, it's very what we call is very a little bit awkward. Yeah, because it just by multiplying with a value and then we can estimate the value for the effect of the uh, dynamic loads. Okay, so for example, for this case, okay, okay, we have a value, okay, for the static plate load bearing test. Okay, we may use the same approach with the one that has been discussed by Jackson and Hadala to predict what will be the value due to the dynamic load. On the foundation racing on the stiff clay and 1.5 meter is diameter are given below. Okay, so here we list all the value of the Q, okay, on the static until 45. Okay, so this is the value of the settlement. Okay, the unconfined compressive strength of this clay is 160. Okay, which is the for the previous one, which is the QU. Okay, which is which is the QU. Okay, so then we minimati which is the CU. Okay, then we will divide with the 2, okay, to get the CU. Okay, so this is the QU. Okay, so then plot a graph of estimate S max over B, okay, versus QD max over QB square CU, assuming a strain rate factor of 1.5. Okay, determine the magnitude of the dynamic maximum dynamic load QD max that produce a maximum settlement S max of 0.15 meter. Okay, so given with B is equal to 1.5, okay, and CU is half from the QU, the following table can be prepared. Okay, so this is the Q value from the static. This is the settlement value. Okay, S over B. Okay, which is the B is the width with the settlement 6.4 in millimeter. So the B is 1,500 millimeter. So this is the value of S. Okay, so Q 4.5 divide with the B square times CU. So this is the value. Okay, and then multiply with the 1.5. Okay, which is the strain rate factor. Okay, in order to estimate for the what we call as for the dynamic loads. Okay, then the next is to plot the graph. Okay, so from the graph, okay, we obtain the QD max over B square times CU with the S over B. Okay, so assuming S over B to be equal to S max over B, okay, and 1.5 QB square CU to be equal to QD max B square CU, a graph can be plotted, okay, as shown in this figure 6.7. Okay. For settlement, okay, the second question, okay, what will be the value of the dynamic, okay, load? Okay, because the settlement doesn't change between the static and also the what we call the dynamic. Okay, that produce a maximum settlement Smax of 0.15. Okay, so Smax is 0.15. Okay, Smax over 1.5 times 100 is equal to 10%. Okay, so from this figure, the value of QD max over V square Cu corresponding to S max over V equal to 10 is about 0.348. Okay, so later on, the QD max, okay, is equal to 0.348 times 1.5 square times 80 equal to 62.64 kilonewton. Okay, so that is the value for the QD max. Okay, where the loads from the due to the dynamic uh, loads. Okay, okay, this is 10%. So then we get the value of the ratio here. So the value of the ratio is 0.348. Okay. So then the QD max is equal to 0.348 times B square, which is B square is 0.1.5 power by 2 times 80, okay, which is the cohesion value, and this is strength value. Then we obtain 62.64, okay. So that is for the clay layer, clay type of soil. Okay. So now, for the seismic bearing capacity and settlement in granular soil. Okay, so this will be the last topic for the shallow foundation. Okay. So figure below show a failure surface is assumed for subsequent analysis under static. Okay, so this is under static, but this is under earthquake. Okay, so we can notice here there is no E, so this is E to represent the earthquake. Okay, according to the theory, the ultimate bearing capacity for continuous foundation in granular soil. Okay, so this is a common type for the static condition. Okay, so we only use the second and the third, okay, sub equation because this is a granular type of soil, okay, without having any C. Okay, so we have Q and Q, Q and Q. Yeah, the difference is only E, earthquake condition. So the bearing capacity factor NQ and K. So this NQ and N gamma we obtain from this table. Okay, the same from the one that we have used before. Okay. Okay. This is the tangent theta. Okay, which is from the earthquake uh, equation. Okay, where we have a horizontal coefficient of acceleration due to an earthquake, KH, vertical coefficient of acceleration due to the earthquake for the KV. Okay. So I noticed this coefficient, okay, when I use the what we call as the GeoStudio, okay, to run for seismic vibration. Actually a vibration, vibration due to the nearest quarry activities, okay, on the slope stability analysis. So I'm using the KH value. Okay, but I guess it's less than the value that commonly from the earthquake, because for the quarry activities it should less 5 millimeter per second, eh, for the explosive activities. Okay, that has been restricted by the DOE, Department of Environment. Okay, so then we found out that there are tangent theta, okay, that need to be used, okay, to estimate uh, the QUE letter. Okay, okay. So this is the another way to determine the NQ and N gamma. Okay, 0 to 120, and also the soil friction angle. Okay, and this is how we may include the value of the tangent theta later on. Okay, to get the value for the N gamma E. Okay, or the ratio between N gamma E and the N gamma. Okay, with the ratio of NQE with the NQ. Okay, so the solid line is referred to the N gamma E over N gamma, while the dashed line is referred to NQE over NQ. Okay, so for each solid line or dashed line, so there is a value of the phi. Okay, for example, this is phi 10, phi 20, phi 30, phi 40. Maximum only up to 40 because that is the common type of phi value. Okay? I guess it's not more than 40 for a common type of phi for a granular material. Okay. So the variation of NQ and N gamma with phi are shown in figure 6.10. Okay, so this is 6.10 and this is 6.11. Okay. Figure 6.11 show the variation of a gamma E and gamma and NQE and NQ with tangent theta and the soil angle phi based on this analysis. Okay, under static condition, the bearing capacity failure can lead to a substantial sudden downward movement of the foundation. However, bearing capacity related to settlement in an earthquake is important and take place when the ratio, okay, tangent theta, okay, reach the critical value. Okay, if kv is equal to 0, then kh over 1 minus kv becomes to kh prime. Okay, if kh asterisk. Okay, so figure 6.12 show the variation of the kh where the kv is equal to 0. Okay, because the earthquake is more related to the horizontal width compared to the vertical width. So the vertical width is normally related to the blasting. I guess we have discussed on the early part. Okay. With the factor of the safety factor as applied to the ultimate bearing capacity equation with P and the width df over b, okay, for 30 and 40. Okay. Okay. So this is the the equation. This is the tab. This is the what we call as uh, the the graph. Okay, but the limitation of the graph. Okay, it only cover for 30 and 40 phi value. Okay, and also df over b to 1 or from 0 to 1 with a factor safety 1 to 3. So this is still can acceptable, can is this a normal value, okay, where the KH is equal to 0 to 0 0.4. Okay. Okay, that is for that is for the 6.12 refer to this KH. Okay. While for the settlement, okay, to predict for the settlement due to the earthquake using a sliding block approach, it can be estimated as SE equal to 0.174, okay, times V square over A times G, okay, times KH over A powered by negative 4 tangent alpha AE. Okay. So the value of KH and AE can be obtained from the same figure and same figure with the previous one. Okay. And also the table 6.5 respectively. This approach can be used to design a footing based on limiting seismic settlement. Okay, so this is the equation for the settlement in granular soil. Okay, so we may use this what we call as this table to find what is the alpha AE. Okay, so okay, this is one of example. Okay, so this will be the last example for the shallow foundations. Okay. A strict foundation is to be constructed on a sandy soil with B is equal to 1.2 meter, dF is equal to 0.9 meter, gamma is equal to 17.6 kilonewton per meter square, and phi is equal to 30. Okay. So determine the gross ultimate bearing capacity, QUE. Assume that KV is equal to 0, KH is equal to 0.176. If the design earthquake parameter V is equal to 0.4, A is equal to 0.32, determine the seismic settlement of the foundation. Use factor safety 3 to obtain the static allowable bearing capacity. Okay. So for the A, okay, so from figure 6.10, okay, this is under, we look on the 6.10, okay, this one, okay. So then, the value of the phi is equal to 30, okay. So then we identify what will be the value of the NQ and N gamma first, okay. So this is the NQ and this is the N gamma. Okay. Why? Because when we want to know what will be the N gamma E, so we need to know what is the N gamma first. Okay. So then we use the figure 6.11. Okay. Determine the ratio between N gamma E and gamma and NQE and NQ. Okay. So then, okay, 16.51 and gamma 23.76. Okay. Then for the tangent theta, okay, due to the KV is equal to 0, then we obtain 0.176. Okay. So then we go for the figure 611. Okay. With the value of the tangent theta is equal to 0.176. Okay. Then we may obtain the ratio between N gamma E and gamma and NQA and NQ. Okay. Okay. So then we obtain NQE and N gamma N gamma E and N gamma 0.4, NQE and NQ 0.63. Okay, those the N gamma E and NQE, okay, will become 9.5, okay, and 10.4. Okay, that is the value of the NQE and gamma E. Okay, then by using the same equation, okay, uh, from the Terzaghi, okay, so then this is not a Meyerhof, this is on Terzaghi, okay, because it doesn't have any shape factor or depth factor, okay, because the what will be the this is for the I guess this is for the stick footing because they only provide the B, okay, not with the length, so we consider it is stick footing. So that is for the value of the QUE. Okay. So if you want to find what will be the QU under static, so you can calculate and then look on the difference. Okay. So for the settlement, for the settlement, okay, TF over B is equal to 0.75. Okay. So from the figure 6.12, okay, we may use this figure, okay. So we obtain D over B is equal to 0.75, 0.75, okay. So then we need to carefully look on the diagram, okay, because from 1 to 0.5, so the value is 0.75, okay, within the range of 1 to 0.1 to 0.5 to 1. Okay, now the fee of the soil in our case is equal to 30. Okay, so the 30 is the solid line to be used. Okay, with a factor safety of 3. Okay, so then we may identify what will be the KH value to be included in the settlement. Okay. Okay, so then the KH value is equal to 0.26. Okay. Also from the table 6.5, by using the KH equal to 0.26, then the value of the tangent alpha E is equal to 0.92. Okay. So we already know what would be the V, A, and G. If I'm not mistaken, they already provided A. Okay, this is A. So G is 9.81. Okay. Okay, G is 9. G is the 9.81. Okay. Okay. So 9.81, tangent alpha is equal to 0.92. Okay. So the rest square 0.26, 0.46 is the KH. Okay, so this is the okay, because they not arranged in on the same with this one. So this is V. Okay, this is okay, while this is V square EG. So the settlement is about 18.7, okay, due to the dynamic load. Okay. Okay. So that's all for the shallow foundation. Okay. So so I finished 2 topics. Okay. Can we continue at 2 o'clock?
Yes, doctor.
Okay. So we take a rest and then might be we will finish by 3. Okay, or less than 3. Okay. Okay. So I need to do something.
By 2 o'clock, doctor?
Yes, 2 o'clock.
Yes.
Okay.
Okay,
Okay,
doctor.
bye.
Thank you.
So we meet at 2 o'clock. Okay, Assalamualaikum and good afternoon.
Waalaikumsalam.
Waalaikumsalam.